In the last video we have seen till the sign convention used in the shear force and bending moment diagram. Now in this video let us see how to draw the shear force and bending moment diagrams. Let us start with a very simple shear force and bending moment diagram. Let us consider one cantilever beam with a point load. Here is the cantilever beam, and let us say its total length is L. Okay, now and the force here is P. Force is P. Now we have to draw the shear force and bending moment diagram for this. To find out the shear force at any location, let us consider a section, okay, and let us separate this part, okay, and place the load as it is. The load is P. Now we know that this part is not moving, that means it is stationary, so this part also must be stationary. So there should be translational equilibrium and also the rotational equilibrium. To have the translational equilibrium, the total forces coming from the top must be equal to the total forces coming from the bottom. So there should be a upward force here to have the equilibrium with the same magnitude P. Okay. Now force is balanced completely. Now this object cannot translate, but it can rotate in the clockwise direction about this point, about the point at which we are considering a section. So to arrest that clockwise movement, we have to add counterclockwise movement of the same magnitude. We are considering this section, let us say, at a x distance from one end, from this end. Okay, so this length is x. So this force P is causing a movement in clockwise direction with a magnitude Px at this location. So the same magnitude we are adding in the counterclockwise direction to make it rotational equilibrium, P into x. Now at this section we got one force and one moment. Now whatever the force we are getting here, we are calling that force as shear force. So the shear force F is equal to P, and the bending moment M is equal to P into x. Okay, this P we are calling as the shear force and Px is the bending moment. From these two equations we can say that the shear force is constant, it is not a function of x, right? So the shear force diagram must be a horizontal line since it is constant. Okay, now in the previous video we have seen the sign convention, right? Since the beam is bending like this and the element on this beam will be subjected to force of this kind, right? This is right face downward, which is positive shear force. Right face downward, which is a positive shear force. So and this magnitude of shear force is P. So if this is the reference line, this is the reference line, okay, our shear force diagram must be like this, a constant over the cross section of the beam, because the shear force is not varying with respect to x, it is not a function of x, this is P. Okay, this is our reference line. Okay, now let us draw the bending moment diagram. This is our reference line, again reference line. Okay, and to draw the bending moment diagram, we have to consider whether the bending is like sagging or hogging. In this case, it is hogging. This is called hogging. Okay, which is considered to be negative. So we have to draw, since it is negative, we have to draw on the downside of the reference line, and the bending moment m is a function of x. Okay, here at this location x is 0, and here at this location x is equal to L. So here the bending moment must be P into 0 here, and the bending moment here at x equal to L must be P into L. This is our P into L. And we are joining these two lines by a straight line. This is a straight line. Okay, we are joining these two by a straight line because it is a linear function. Okay, if it is x square, we have to join by a parabola. Okay, this is about the shear force and the bending moment diagram for a cantilever beam with a point load. Now let us see the shear force and bending moment diagram for uniformly distributed load, like this. Okay, and this is the length of the beam, which is L, and this is the load intensity. We are calling that one as the load intensity, small w. It is denoted by small w. To find out the shear force and bending moment in this beam, let us consider the procedure is same. We are considering a section here at this location. At a distance of x, we are considering one section. So I'm just redrawing this line, this section. Okay, this distance is x, and this is the only load we are having. Okay, so and we know that this portion of the beam is neither translating nor rotating, so we have to make it equilibrium. To have the translational equilibrium, we need to balance the forces. total force coming from the top is W into X. Total force coming from the top is nothing but the load intensity into distance is the force. Actually, that much force we are adding here. W into X, small w into X. Small w is the load intensity per unit length, and if you multiply this load intensity with the distance, we will get the total load in newtons. Okay, now the force is balanced. Now we have to balance the moment. Okay, now this beam will not translate because force is balanced, but it can rotate, right? And about this point it can rotate due to this load. Okay, whatever the load this UDL is creating in clockwise direction, the same moment we have to add here in the opposite direction. The total moment created by this moment, uniformly distributed load is equal to the total load, that is Wx, into, and this total load is considered to be acting at the center of gravity of this load, that is exactly in the middle of this load. Okay, you can assume that this entire load is acting at the center of gravity, so the distance from this point to that center of gravity is x by 2. This is the total moment it is creating, W, excuse me, that is x by 2. It is actually Wx into x by 2. I will just redraw this entire thing. We are adding a counterclockwise moment of magnitude W into x square by 2. Wx into x by 2. This is x by 2 actually. Excuse me for that. Now at this location we got one force and a moment. This force we are calling as the shear force and this moment as the bending moment. So the force F is equal to, here in this case, is W into X, and the moment is equal to W into x square by 2. X square by 2. Now we can draw the shear force diagram. Okay, here also the beam is bending like this. Just observe my cursor. Okay, and the element will be subjected to this kind of load, right face downward, which is considered to be positive. So I am drawing on the positive side of the reference line. Okay, here at this location x is 0, and here at this location x is L. So the shear force here will become, F will become 0 here. Here it is W into L, and these two are joined by a straight line. Since it is a linear function, this magnitude is W into X. Okay, now let us draw the bending moment diagram. The bending moment diagram, here x is equal to 0, that is 0 here, and here x is equal to L, so the bending moment here is m into L square by 2. Here it is m into W into L square by 2, W into L square by 2, and we have to join these two by a parabola because this is a function of order 2. Okay, so this is a parabola, and this is a straight line. Okay, here actually one important thing we have to observe in this case is we can also draw something like this. We can draw the same diagram like this also. This also can be considered as the parabola, but we are not drawing like that. It is because we know that dm by dx, dm by dx is equal to f. Similarly, df by dx is equal to the loading diagram. This one we are calling as the relation among the bending moment, shear force, and the loading. Okay, if you derivate the bending moment diagram, you will get the shear force diagram. If you derivate the shear force diagram, you will get the loading diagram. Okay, if we observe that here this parabola is having a zero slope here, that means if you derivate this parabola at this location, you will get a 0, that is matching here. Okay, and the derivation of this bending moment diagram at this location is nothing but the slope here. It is having some finite slope, right, of WL square by 2, right? So at this location, if you derivate this WL square by 2, you will get W into L, same as this one here, W into L. So this is W into L. Okay, but here in this case, if you draw the parabola like this, it will have a finite slope here. That means here in the shear force diagram you should have a positive value, but it is not so it is the wrong shear force diagram for this. So the correct shear force diagram is this one, like this. Okay, now let us see the shear force and bending moment diagrams for simply supported beam. Let us consider a simply supported beam with a point load. And with a middle load which is P. And this total length of the simply supported beam is L, and this load is acting at a distance of L by 2. Okay, If the load is acting in the middle, we can say that this load will be shared by these two supports equally. So here, since this is a simple case, there is no need to calculate the reactions. Here we can write directly, which is P by 2 and P by 2. Okay, and the deflection curve here is something like this, right? So this part of element will be subjected to force like this, and this part of the beam is subjected to force like this. Okay. If you see the sign convention yeah, that is used in the drawing of the shear force diagram, if it is right face downward, which is considered to be positive, this is positive and this is negative, this part is negative, this part is negative. So the shear force at this location is nothing but the algebraic sum of all the forces on either side of the beam. Okay, here in this case, you can say that this P by 2 itself is the algebraic sum of all the forces. Okay, you can actually consider either side. If you consider this side, this is P by 2, this side also algebraic sum will become P by 2 only, because this is plus P and this is minus P. Okay, this is plus P and this is minus P by 2. Okay, and the net sign of the shear force diagram must be positive here in this case and negative here in this case. So our final shear force diagram will be like this. Since this is positive, it will continue till here, and here we are having negative shear force of same magnitude. If I want the shear force at this location, I can consider this side of the beam, right? Because it is easy, this section is nearer to this side, and the algebraic sum of all the forces on this side of the beam is nothing but the P by 2 itself, and from here we can say that it is a negative nature. Okay, so it is P by 2 with negative sign. So this will become the shear force diagram where it is positive and here it is negative, and this is our reference line. Okay, now coming to the bending moment diagram. Here at this location the bending moment is 0. Okay, and the bending moment here at this location is nothing but this force into this distance. This force is P by 2 and the distance is L by 2, so we will get P into L by 4, right? P into L by 4, and this is positive because it is actually, the beam is actually sagging, sagging, which is positive. And here also it is the similar case. It is like this, and the magnitude here at this location is P into L by 4. This is the bending moment diagram for a simply supported beam with the point load. Okay, and one more thing we have to observe in this while drawing the shear force and bending moment diagram is if the shear force is 0, the bending moment is constant line. This is called constant. Okay. If the bending moment is constant, if the shear force is constant, the bending moment will be uniformly increasing or a straight line. Okay, this is actually x power 0, which is constant, and if it is x power 0, it will be x power 1. Okay, this is what the linearly varying. If it is linearly varying, if the shear force is linearly varying, the bending moment will be parabolic. That means the since it is linearly varying, it is x power 1, and it is parabolic x power 2. If it is parabolic, it is a cuboid. You can see even more curvature. It is called cuboid. Okay, it is x power 3, and here it is x power 2. So the bending moment is 1 degree higher compared to the shear force always. Since this is constant, you will get a linearly varying in the bending moment diagram. Just remember this. Okay, now let us see one more example. Shear force and bending moment diagram for a uniformly distributed load. Let us say its load intensity is small w and the total length is L. Okay, now this total load is, now we have to draw the shear force and bending moment diagram for this beam. Okay, now this load or total load coming from the top is the load intensity, that is W, Newton per meter. Actually this is Newton per meter. This total load intensity into length, that will give the total load coming from the top, which is shared by these two supports equally. So the reaction at this location will become total load, that is WL by 2, and here also WL by 2. Now total load coming from the bottom is WL by 2 plus WL by 2, which is WL, which is equal to the total load coming from the top, that is from the top. Okay, now let us try to draw the shear force and bending moment diagram for this. Okay, and we know that it is bending like this, and the section here will be subjected to this kind of load which is negative. This can be considered as negative, right? Okay. This is our reference line, and we know that the shear force here at this location, wherever the point load is there we will get a vertical line in the shear force diagram, which is equal to WL by 2 here, in this case WL by 2, since it is positive because it is subjected to load something like this. Okay, this element is subjected to load something like this, and here it is like this. So if the right face downward, it must be positive. Okay, here we have the negative. Since it is negative, we have to draw a vertical line of the same magnitude whatever is there, W into L by 2, and we can join these two by a straight line. Really, this is a straight line. Let me write this straight line. Okay, this is the shear force diagram for this. And coming to the bending moment diagram, since this is the sagging, our bending moment diagram must be positive. Okay, so we have to draw on the top side of the reference line, and the bending moment here at this location, if we want to find out the bending moment at this location, the bending moment due to this load is nothing but W into L by 2 is the total load into distance. Here we want to find out the bending moment, right? So we have to measure the distance from here to here, which is L by 2. Load into distance minus we have to consider this much load. How much is that? That load is nothing but W into L by 2. W into L by 2 into this entire load is acting at the center of gravity of this load, this half load, which is L by 4. This is nothing but WL square by 4 minus WL square by 8, which is WL square by 8. Okay, that is the maximum bending moment here. Okay, and these 2 points will be joined by a parabola like this, and this maximum magnitude is WL square by 8, WL square by 8. Okay, here also we are drawing the parabola like this, but not like this. See, this is also parabola, right? This is also parabola. We are not drawing like this. It is because if you derive this curve, you should get this curve, right? It is having a some finite slope here, like this. Okay, and the slope here is like this. Wherever you want to find out the slope, just draw a tangent at that location and see how much angle it is making with the positive x-axis. Here it is theta. Okay, tan theta is the slope here, which is a non-zero number, which is a positive number. We should get that number here, which is W into L by 2. But here in this case, if you draw a tangent, it is a horizontal line. It is a horizontal line. So at this location also we have a zero slope here, but it is not the case here. So the bending moment diagram must be like this only. This is the wrong one, this is the correct one. And here also if you draw the tangent here, you will get a horizontal line. That means the slope of this curve at this location is 0, okay, which is matching here, right? Now let us try to do some of the examples of the shear force and bending moment diagrams. For example, a beam is there like this, a cantilever beam. Okay. At 1 meter distance, we have a clockwise moment m. At a 2 meter distance, we have a counterclockwise moment 2m. Now we want to draw the shear force and bending moment diagram for this. Okay. To draw the shear force diagram, the shear force at any section is defined as the algebraic sum of all the forces on either side of the beam. If I consider on the right side of the beam, there is no force at all, only moment is there. So the shear force at any section must be 0. So the shear force, there will be no shear force in this beam. It is a 0, entirely it is a 0. But coming to the bending moment diagram, this is our reference line. And since this bending moment is having more influence, since it is only m and here it is 2m, right? So this portion will be bending something like this at the end, which is forming sag. It is called sagging, right? This is sag. If it is like this, it is sagging, which is positive, and if the beam is bending like this, it is hogging, it is negative. Okay, here in this case it is going up like this, which is positive. So wherever the moment is there in the bending moment diagram, at that location you should get a vertical line. Okay, similarly, wherever the force is there in the shear force diagram, you should get a vertical line. Here there is no force, so there is no vertical line here, but here moment is there, bending moment is there. So, and we know that it is a positive bending moment, since it is bending like this, positive bending moment, and here we are calling as 2m. Okay, and it will continue, this 2m will continue till this location. Okay, and this moment is having a nature opposite to this kind of moment, right? So the moment will reduce here by an amount m, just m. Okay, this is m, and this same moment will continue till here. Okay, so here we are starting with 2m, and that 2m will continue till this location, and here at this location the bending moment is reducing by m, because it is having opposite nature compared to this 2m. Okay, and this m will continue until this location. Here also the bending moment at this location, you have a vertical line of the same magnitude m. Here 2m is there, so we have a vertical line of same magnitude. This completes the shear force and bending moment diagram for this kind of loading diagram. Now let us see one more example. Let me consider a simply supported beam like this. We have two supports and this entire beam is divided into three parts. Here we have one more support. We have two loads, 15 kilonewton here. So this is kilonewton. And here also we have some 20 kilonewton force is there. Okay, now we want to draw the shear force and bending moment diagram for this. The lengths given are something like this. This is 1 meter and distance from here to here is 1 meter and distance from here to here is 1 more meter. Okay, we don't know the reactions, we are calling them as RA and RB. In the simply supported beam, the first step is to find out the reactions if they are not known. Okay, the equation here is the total load coming from the top must be equal to the total load from the bottom. So is nothing but the upward force must be equal to the downward force. The total downward force is 35 kilonewtons, that is 20 plus 15, that must be equal to RA plus RB. So our first equation is RA plus RB equal to 35. And to get one more equation, let us find out the let us take the moments about this point. Okay, let us call this point as A and this point as B, and if we take the moment about point A, which must be equal to 0, this 15 is causing clockwise movement about this point MA, right? So this 15 into 3, which is a clockwise moment, plus this 20 is also causing clockwise movement about this point, like this. So it is 20 into 1, 20 into 1, which must be equal to this RB is causing counterclockwise movement. So this is RB into the distance is 2 meters. This is our reference point about which we want to find out the moment, and this is the force. So the distance from the reference point to the force is 2 meters here in this case. This is 2. This is RB into 2. Okay. So it is becoming 65. RB is 65 by 2. RB is 32.5. If it is 32.5, RA must be 2.5. RA must be 2.5. 2.5 kilonewtons. So total entire load is going to RB only. Here we have 32.5 and here we have 2.5. Okay, now we got the reactions. Now we are ready to draw the shear force diagram. Okay, at this location the beam is going like this, right? Beam is going like this, which is the element is subjected to load something like this, which is a positive right face downward considered to be positive shear force. So this 2.5 is causing a positive shear force. So this is our reference line. Okay, this 2.5 is causing the positive shear force, which is 2.5, and it will continue till here. In the shear force diagram, wherever the point load is there, at that location we should get a vertical line of the same magnitude. Okay, here 20 kilonewton force is there, so we should get a vertical line of the same magnitude, that is 20 kilonewton. Okay, 20 kilonewton. So this length of this line is 20 kilonewton. Okay, so the shear force at this location will become 17.5. 17.5 here, from here to here with a negative sign, and 2.5 here, so that the total length of this line is 20 kilonewton. Okay, and this will continue till this point B. This shear force will continue till the point B. Okay, here at this location see, due to the due to this force we got up, and due to this force we got down, and due to this force we have to go up. Okay, because this is its force, its nature is just opposite to that of this 20 kilonewton. Okay, for example, if we are going downward only, for example this RB direction is downward, then we have to further even go down, but here it is going up, so we have to go up by the RB magnitude, whatever is that. So since it is 32.5, we have to climb 32.5. Already 17.5 is there, so here we will get plus 15. Okay, this is the plus 15, and here it is 17.5. so the total length of this line will become the plus 15 kilonewton, and that will continue till this location. Okay, and we are just closing this. If we draw the shear force diagram correctly, this plus 15 should match with this plus 15. Okay, This at this location we have a point load of 15 kilonewton, the same 15 length of vertical line there should be. Okay, so this is the plus 15 kilonewton. This completes our the shear force diagram, where this part of the beam is subjected to positive shear force, this part of the beam is subjected to negative shear force, this part of the beam is subjected to again positive shear force. That means this this part of the beam is like this, and here also this part of the beam is like this, but here in between there is a possibility of getting shear force like this, so we got negative here, is positive. Okay, now let us try to draw the bending moment diagram. Okay, here at this location we have a zero bending moment, here we have a zero bending moment, and the bending moment here at this location is nothing but this RA into this distance. And since it is bending like this, which is it is bending like this at that end, right? This is bending like that due to this RA, and this can be considered as a sagging, which is positive bending moment. Okay, so the bending moment here at this location is this RA into 1, which is 2.5. Okay, and the bending moment here, if I want to find out, that can be found from here at this location. Since this part is bending like this, right, like this, which is hogging can be considered as negative. Okay, let me just erase this. Since it is bending like this, which is considered to be hogging, so we have to draw negative side of this, and the bending moment here at this location must be equal to this force into distance, which is 15 kilonewton meter. Here at this location 15 kilonewton meter, here it is 2.5 kilonewton meter, and this one also we are joining by a line, because it is a since it is a constant line, we should get 1 degree extra, that is uniformly varying line, linearly varying line. Okay, and once we got these 2 points, at this point we got 2.5, which is positive, and at this point B we got 15 kilonewton meter, which is negative. Okay, and in between this portion also we got a constant line, so we should get a inclined line. So these 2 points can be joined by line like this. Okay, here we are getting a zero bending moment. Okay, this point we are calling as point of contraflexure. Point of contraflexure. Point of contraflexure is nothing but a point of a point on the beam where bending moment is changing its sign, that is either from positive to negative or negative to positive. Okay, generally we will find the point of contraflexure in the beams where both sagging and hoggings are both are there. If both are there, in those cases we will generally find this point of contraflexures, because here in this location we are getting a sagging, but here in this location we are getting hogging. Hogging is negative and sagging is positive. Here it is positive and here it is negative. So there should be a crossing point while coming from the negative to positive. So in those examples we will get this kind of point of contraflexure. But if you see in case of the simply supported beam with a simple point load, we will get, since this is sagging, we will get a positive bending moment, and the bending moment diagram will be something like this. Okay, here we are getting zero bending moment, but we are not calling this 0 point as the point of contraflexure, because it is not crossing from from negative to positive or positive to negative, but it is just a zero bending moment point. These points are not the point of contraflexures. Similarly, this point is also not the point of contraflexure. This point is also not the point of contraflexure. But this is the point only where the bending moment is crossing its sign. Okay, generally we get point of contraflexures in the overhung beams like this. In general, if it is a general simply supported beam, we will not get this point of contraflexure, that is crossing in the beam. Okay, and our next challenge is to find out the distance of this point of contraflexure. Distance, what distance it is there, we want to find out this distance. Its distance is x. Okay, let us say this distance is x. Now at this distance we know that the bending moment is 0, right? This point is somewhere around like this. At this point we are getting a 0 bending moment. That means this 2.5 is causing one bending moment in the clockwise direction, and this 20 kilonewton is causing a counterclockwise bending moment. Okay, at one location these two must be equal. So at this location, I'm just extending this point. At this location the bending moment must be 0, right? So RA into X, RA is 2.5 into X must be equal to this 20 into this distance. This distance is nothing but x minus 1. X minus 1. If we solve this equation, we will get 17.5 into x is equal to 20, and x is equal to 20 by 17.5, which is 1.14 meters. This is nothing but 1.14 meters. So this distance from here to the point of counterflexure is 1.14 meters. This 1.14 meters. This is also generally asked questions in both GATE and IES exams.